Hello, welcome to Engineers Mindset. All right, so we have been undergoing a series on centroids in strength of materials or solid mechanics. Okay, so let's examine this question. It says we should determine the moment of inertia for the inverted T section shown. Okay, so the essence of undergoing that series on centroids was actually to lay a foundation down to where moment of inertia, because we are still going to need to determine the centroids before we can be able to find out moment of inertia. Okay, so I'm going to use it to actually explain what moment of inertia is and how we can find them. There are two basic methods of obtaining or determining moment of inertia for any composite section. The first method is actually the parallel axis theorem. Okay, so we are simply going to make use of that theorem to determine the moment of inertia for this section. The second method is actually the perpendicular axis theorem. Okay, but that method is a little bit tedious, so we're not going to be talking about it now. But for this video, we're going to use the parallel axis theorem to explain the moment of inertia for this section. All right, so without further ado, let's get to it. So the very first thing to do, as always, is to first of all obtain the centroids for this given section. So please look up my centroid videos for proper understanding of how you're going to find these centroids. But in my videos, I said before you're able to carry out the centroid of this shape, you have to first of all bisect this shape. Since I have an inverted T section here, notice that if I cut here into two, I will now have two different components. This is component one, so I can call this component one. That has two rectangles now, and this is rectangle two, simply because I've bisected this side. So if I do this, I find out that this is actually what? Two rectangles on top another. Okay, and if that is done, it means now that I need to find this height from this point down to this point. Since I've been able to bisect these rectangles into two, so it means I need to now obtain the height of what? This other rectangle, AB. Okay, so if we examine the figure, notice that from F to E, which is this depth here, is 20 millimeter. Meanwhile, from the top here down to this depth is 50 millimeter here. So which means in order to obtain distance from this point to this point, or the depth of this other first rectangle, it means I will simply what? Remove 20 millimeter from 50 millimeter. That simply gives me 30 millimeter. So it means the height or the depth of this first rectangle is simply 30 millimeter. Okay. Okay, not forgetting to this width is given as 50 millimeter. Okay, please don't forget. All right, so this width is given as 50 millimeter. That's simply from D to E. Okay, that's 50 millimeter. All right, so that's the very first thing. Segment them into what? Different components, their respective rectangles. Once you're done with this, you create a table. The shorter and better method is by what? Using table to find the centroid. So the first thing we have to do is to obtain the centroid. So we'll create a table. Okay, the first column is for the what? The component or rectangles, whichever one you choose. Okay, for the components that we've obtained so far. So we have about two components here, the first rectangle and the second rectangle. So we'll simply call that component one and component two. Okay, which is simply what this. Okay, after the components, the next thing to do is to create another what? Column for the area. So you obtain the area of each of these components. The area should be in millimeter squared. Okay, the area should be in millimeter squared. So you're not converting, so area should be in millimeter squared. So you're not converting, just simply leave the units the way it is in millimeters and work with them like that. So for the first component, which is the first rectangle, area is simply what? The width times the depth. The width here is 20 millimeter, the depth is 30. So we simply have 20 by 30, and that will simply gives us 600 millimeter. So the area of the first segment is 600 millimeter. For the second segment, the width is given as 15 millimeter, the depth is 20 millimeter. So the area is simply 50 by 20, and that's simply 1000. So we simply have 1000 millimeter squared. So after obtaining the area of these segments, next thing is to simply what? Sum them up. So you simply have summation of area, sum the areas up, and it will give you a value. So you simply sum them up. If you sum these areas up, 1000 plus 600 simply gives you 1600 millimeter squared. So that gives you the total area for each of those components. Okay, so after obtaining the areas, next thing to find is what? Centroid distance. Okay, so we obtain centroid distance x and centroid distance y for each of the segments. So we start with x. So we obtain the centroid distance x. Okay, so we'll find the centroid distance x for each of the segments. We'll find the central distance x for each of the segments. Okay, so to find the central distance, I always say, before you can be able to find the central distance, you need to first of all obtain your reference line. And I said the reference line is the line, the ground bottom, or the very last shape or line on what that makes up the whole segment. So this whole segment now has a very large shape where at D and E. So this DE now is the reference line DE, which is the very last figure or shape that makes up the whole system. That's the ground base. So DE is the reference line. So whatever we do, we must always take everything down to the reference line to find the central distance. I also explained that just like we have in a two-force system, I said here is simply where y and this is simply what? Your x. So it means that if I relate this to this each of these shapes, the vertical lines represent where my section, which is the y direction or the y segment. Now I'm looking for central distance x. So which means I'm only going to bisect the x segment, and the x segment is simply where the width. So for each of the shape, the width represents the x segment and the depth represents the y segment. Okay. So for this shape now, this width represents the x segment. Meanwhile, for this shape, the width itself represents the x segment. Meanwhile, this height or this depth represents the y segment, and this depth represents the y segment for what? This other shape. Okay. Having that in mind now, centroid distance simply means, centroid actually means bisecting into two. So I want to find the central distance for what? The very first shape. It means I have to bisect the x segments into what? Two. And the x segment for the first shape is simply the width, which is A to B. So bisecting this into two, let us now obtain the central points. That's the center of mass. Let's say we trace these points down to this point, trace this side and join them here. This is now the center of mass. Now I want to bisect. I want to bisect the S segment for what? The first shape into two. This is simply what? Cutting this plane into two. This is the X segment for the first shape. So cut that plane into two. Cutting that plane into two simply means you are dividing the width, which is 20 millimeter by 2. So you simply have a 20 divides by 2. But it doesn't end there. After cutting this shape into two, you need to what? Take it down to the what? Reference line. So watch, cutting here into 2 is same as cutting this point into 2. That's simply bisecting 20, because this is also the width for that first segment. So simply bisecting 20 into 2. So if I bisect 20 into 2, I will simply have 20 divided by 2 here and 20 divided by 2, which is simply 10 and 10. But then that is what? Cutting this point into 2. I have to take it down to the reference line. Like I said, you always take all of them down to the reference line. So moving from this point to the reference line, I have covered what? This height of 20 millimeters. Everything you do must always get to the reference line. So bisecting this into 2, that's 20 divided by 2, I will still take it down to the reference line, which means I'm covering this height to get to the reference line, 20 millimeter. So you simply add that height to where? The first shape. So plus 20, and this will simply give you, of course, 20 divided by 2 is 10. 10 plus 20 simply gives you 30. So this is actually 30. So central distance x for that first shape is 30. The same thing happens here. Locate this center of mass for this first shape, although it's not necessary, it's not a mandatory thing, but just a thing to note. Now I want to find the central distance x. So I said the width always is what? The segment x. The width always, and the width for this figure is simply where? From C to F or from D to E. This is the width, and it's given as 15 millimeter. So if I bisect this width into 2 simply by cutting this plane into 2, that's dividing 50 by 2. Notice that that division actually takes me straight to the reference line. So I don't need any other height to get to the reference line. I've already cut this into 2, dividing the width into 2, which is simply what? 50 all over 2. I'm already at the reference line. So that means for that segment, I will simply have 50 divided by 2. And that's simply what? 25. So this becomes the central distance x for the second shape, and this is central distance x, 30 millimeter for the first shape. So that's the first thing to do. Next now is to find the central distance y. So we now find central distance y. Okay, central distance y, distance y, central distance y. So same thing for both the first shape and the second shape. We obtain the central distance y. Okay, so like I said, the depth represents the y segment, while the width represents the x segment. So this depth now represents what? The y segment for this shape. So if I want to find the central distance y, it means I have to cut this depth into 2. And this depth is given as what? 30 millimeter. So it simply means I will have 30 divided by 2 for the first shape, 30 all over 2. But it doesn't end there. 30 divided by 2 is simply what? Cutting here into 2. That's from here to here becomes 15. While from this point to this point becomes 15. So I actually cut from here down to this point, and I'm not yet at the reference line. So after bisecting this into 2, it took me down to this point, because from here to here is 15, from here to here is also 15. So which means I need to take it down to the reference line, like I always say. Whenever you bisect, bring everything down to the reference line. So taking this down to the reference line, I also cover this height of 20 millimeter. So simply add that height towards the first shape. So I'll simply have plus 20 millimeter. That's plus 20. And this actually gives me now 30 divided by 2 is 15. 15 plus 20 is simply 35. So I simply have 35. And finally, for the second shape, see the same thing. The y segment now is what? Now the depth. And this depth is given as 20. So notice now that if I cut 20 into 2, that's 20 divided by 2. From this top to this point, from the middle to this point is 10. From the middle down here is 10. So I'm already at the reference line. Okay, I'm already at the reference line. Needing no other height to get a reference line. So I simply have that section to be what? Central distance to be 20 divided by 2. And this is actually 10. Okay, so this gives me the central distance x and central distance y. So I said after obtaining the central distance, the next thing to do is to obtain the product of the area and each of the central distance for each of the shapes. So for the first, I will have product of the area times central distance x, and then I'll have product of the area and central distance y. So we'll do that now and see. The first area here is 600. The first central distance x here is 30. So we'll simply obtain 600 by 30. Okay. 600 by 30. And that will simply give us, that simply gives us 18,000. Okay. The next is to obtain central distance for the second shape, 1000 by 25. That's around 25,000. So we simply have the next one, 1000 by 25, which gave us 25,000. Okay. So that gives us 25,000. So all we need to do at this point is sum these products together. Summation of AS, summation AS, sum these products together. So we simply have 18,000 plus 25,000. Okay. And that simply gives us 43,000. So we have this. Next thing to do is also what? Obtain the product of area of each of the segments and the central distance y. Okay. So we obtain the product of each of the areas and the central distance y, just like we did in the first case. So it becomes now 600 multiplied by 35 for the first segment. We have 600 multiplies 35. Okay. That gives us 23,000. Okay. And then for the second segment, we have 1000 multiplied by 10, which is central distance y for the second segment. 1000 multiplied by 10, that gives us about 10,000. Okay, so as usual, sum them up, obtain summation of area, product of area and y. If we sum that up, we're simply going to have 43,000. So we simply have 43,000. Okay, that gives. All right, so if we have that now, we can now find the centroids. Okay, so centroid in the x, centroid x, simply x bar. This represents the centroid in the x-axis, x bar, and that's simply giving us what? Summation of the product of the area and central distance x all over summation of the entire area. So this is now equal to summation ax gave us 43,000. So we simply have 43,000 all over summation of the area, which is 1,600. 1,600. So this simply means that centroid in the x-axis, which is centroid x, is simply 43,000 divides 1,600. That gives us 26.875 in millimeter. So it is obvious. Centroid in the y, okay, centroid y is still the same thing. Summation of area times y, central distance y all over summation area still gives us 43,000 all over 1,600, and that still this simply implies y bar is simply equal to 26.875 millimeter. Now it is clear here that you can see that the both centroids are equal, and the reason why they are equal is simply because this beam is symmetrical in both the x and in the y. Now what does it mean for a beam to be symmetrical? If I bisect this beam in the y-axis, like I've cut here now into two, notice that from this point, from A to the point of section becomes 20 divided by 2, which is 10. Also from B to this point of section becomes 10. And from C to the point of section becomes 50 divided by 2, which is 25. Same thing happens here. From F to the point of section becomes 50 divided by 2, which is 25. So I will have an even shape, something like this. Okay, something like this. I will have something like this having the same values, have something like this having the same values, something like this. So this is what makes up the shape, and they are symmetrical about what? The y direction. They are symmetrical about the y direction. So it simply means that the centroid in the y will be equal to centroid in the s. So it's symmetric. Since they are symmetric, they will have equal what? Section centroid. They will have equal centroid. That's why we're having those centroid values to be equal. Okay. But then the question is to find moment of inertia. Okay, so the question is to find moment of inertia, and we want to employ the parallel axis theorem to find the moment of inertia. So we've known the centroids, we want to employ the parallel axis theorem to find the moment of inertia. So, okay, so to find the moment of inertia, this is what we'll do. I will pick out these values of centroids and keep them here because I need to make space for myself on the board. So picking out the values of centroid, I had x bar, okay, to be equal to 26.875 millimeter. Also, I had y bar to be equal to 26.875 millimeter. Okay, I can wipe here now. So I said to determine the moment of inertia, the parallel axis theorem is simply the best approach to it. Now, what is this theorem? Using parallel axis theorem, okay. Okay, so since we have more than one shape making up the segments, that's shape 1 and shape 2, then the moment of inertia Ixx for the x direction is simply equal to Ix x1 plus Ix x2. where ixx1 is simply the moment of inertia for the first shape, and ixx2 is the moment of inertia for the second shape in the x coordinate or in the x direction. The next theorem is also what I is equal to y1 plus y2. So this is also the moment of inertia in the what y-axis. While this is moment of inertia for the first shape in the y-coordinate, and the moment of inertia for the second shape in the y-coordinate. So let's now obtain what these different coordinates for the first shape and for the second shape. Now, Ixx1, this is the parallel axis theorem, please. This is the parallel axis theorem. Now, Ixx1, like I said, is simply the moment of inertia for the first shape, which is this. And what is this? What is this moment of inertia? Is simply what? The width, which is b, times the depth cube all over 12. This is the moment of inertia for every rectangular section. But now we have a composite section. So we simply have, for the first shape, bd cube over 12 plus the width b times depth, now multiply by central distance y, subtracting centroid of the y, and then squaring this what bracket. So you have this will be the moment of inertia for the first shape. So notice this transposition now. We are considering x. Since we are considering x, we have bd cube over 12 for the first segment plus that same width times the depth of that same segment. But now, since we're talking about moments in the xx coordinates, we simply multiply bd by what? The difference in the central distance and the moment, the difference in the central distance and the centroid in the y direction for that first segment. So it can also be the centroid minus central distance. It doesn't matter. So far there's square there, any negative sign here can cancel. So take note in that transition is simply ixx1 equals bd cube over 12. It remains the width, the depth of that first material cube all over 12 plus the same width of that material, the same depth of that material. But now you're multiplying these two products by the difference in the central distance in the y direction and what the centroid in the y direction. That gives you the moment of what? Moment of inertia for the first segment. Okay, so this is actually equal to, okay, let's do this here now. This is now equal to, we said bd cube. Okay, we said bd cube, and b is the width for the first shape. This is the first shape. The width is 20 millimeter, so simply put down 20. Please also do not convert to meters, keep it as what? Millimeter. You have 20, then d here is what? The depth of the first segment, which is 30 millimeter, so simply 30 cube. So 20 by 30 cube, okay, all over 12 plus, we now said bd, so simply the width times the depth, which is simply 20, okay, by 30, now multiplies by the change in the central distance y and centroid in the y for the first segment. So we look now at the first segment. This is central distance y for the first segment is simply what? 35. Remember the first shape or first component. And then this is centroid y for the first shape. Centroid y for the first shape. Okay, we have the same value, 26.875. So we simply what? Subtract those two values together. Central distance y is 35. You simply have 35 minus 26.875. Simply what? Square this term. So you have this. Okay, so ixx1 is now equal to, so let's evaluate this now. This becomes 20 by 30 cube is 27,000 all over 12 plus, here you have 20 by 30, 20 by 30 here, which is 600 into, of course, 35 minus 26.875, that's 8.125 all squared. Okay, so if we evaluate this now, we are having 20 multiplied 27,000 divided by 12. Okay, that gives us 45,000. Okay, plus, now I have here 600 multiplies 8.125 squared. So let's do that and see. That actually gives us approximately 39606. 39606. Okay. All right. So the first moment of inertia or moment of inertia for that first segment is simply 39606 plus 45,000. That's 84,606 in millimeter for. So please take note, moment of inertia is always measured in meters for, but in this case, since we are using millimeter, it becomes in millimeter for. Okay, so the moment of inertia for the first segment, Ix1, is simply 84606 millimeter 4. So this becomes the moment of inertia for the first segment. So this part is solved. Next is to find the moment of inertia for the second segment in the x-axis. Still what? The same theorem. So let's keep this moment of inertia one side. Okay. So I'm going to wipe out this question now. All right. So Ixx1 is simply 84606 millimeter 4. So let's find for the second one now, Ixx2. All right, so it's still the same thing. It doesn't still change. Only that this becomes what? Ixx2. Since we are still on the x, everything here, the formula remains the same. Now it's going to be what? Y minus y bar for what? The second segment. That's the only difference. And of course, BD cube here has to be for the second segment as well. Everything still remains the same. But notice that if you're looking for the moment of inertia for the second x segment, you have to subtract in this bracket central distance y and centered in the y. So it has to be y minus y bar. So if you're doing for y, then here has to be what? X minus x bar, or the same order, everything remains the same. Let's try it now and see. So we have BD cube over 12. B is the width, and for the second segment, the width is simply what? From D to E, which is 50 millimeter. So you simply have 50 by the depth. The depth here is what? This height, which is 20 millimeter. So depth cube becomes 20 cube times 20 to the power of 3 all over 12. Okay, plus we have here the width times depth, so become 50 by 20, 50 by 20. So multiplying by what? Y minus y bar, central distance y for the second segment. This is the second segment or the second component. Central distance y is 10. So it becomes 10 minus centered in the y, which is simply 10 minus 26.875 all squared. So once again, I said, since this is squared, it doesn't matter which comes first. If you have a negative value, the square of that negative value will automatically become positive. So it still remains y minus y bar, or it can be y bar minus y. Anyone can subtract anyone. You will still have a positive value as the answer. Okay. All right. So Ixx2 is now equal to, so let's obtain now, this is now 50 by, of course, 20 to the power of 3 is simply 8,000 all over 12. Okay, plus 50 by 20 here gives us 1,000. Okay, into 10 minus 26.875, of course, will give us minus 16.875 all squared. So once again, it doesn't matter anyone that subtracts. So far you have square here, if there's a negative sign inside, it will always eliminate the negative sign. So this is now equal to, so let's now obtain 50 by 8,000 divided by 12. So that gives us approximately 3, 3, 3, 3, 3. Okay, you have this plus, now you have 1000 multiplied by 16.875 squared. That gives us approximately 2 plus 2 uh, plus 284770. So if you add that together, you simply have 284770 plus 33333. So that gives us 318. Okay, 103. All right, so the moment of inertia for the second segment, Ixx2, is simply 318,103 millimeter to the power of 4. That gives us Ixx2. So we can put that down here. x2 equals 31810 millimeter 4. Okay, so this becomes ixx2. So from the parallel axis theorem, simply sum the two moment of inertia. That gives you the moment of inertia for what? This composite segment in the x direction. Let's do that now and see. All right, so from the parallel axis theorem, which is this, the moment of inertia in the x coordinate is simply what? Ixx1 gave us 84606. We'll have 84606 plus Ixx2, which is 318103, 318103. So this simply means Ixx is simply equal to simply 402709 millimeter 4. Okay, so this becomes the moment of inertia in the x coordinate. Okay, so let's try to obtain that for the y coordinate and see the difference between the two. Not much of a difference. Okay, let's try it and see. From parallel axis theorem for the y coordinate, it's still the same thing like I said. You have y, which is moment of inertia about the y coordinate is simply y1, since we have just two segments, plus y2. Okay, so if you have more than two, of course you have to add the third one. Okay, so let's now find what is y1. So please pay attention here now. y1. Now the difference now is that when we did for the x direction, we said this is our width, while the y is simply what? Our depth. Please take note. When we found moment of inertia for the x coordinate, we simply said x is our width, meanwhile y is our depth. So if we are now looking for moment of inertia for the y coordinate, so take note, y is going to be what? Your depth. Sorry, y is going to be your width, and x is now going to be your depth. Please take note of this difference. If you're not doing the moment of inertia for the y coordinate, it simply means now that y is going to now be your width, meanwhile x will be your depth. So the equation will now be, instead of bd cube over 12, it becomes db cube all over 12 plus db times. Now, since I'm talking about y, it means the central distance x and the centroid of x have to subtract each other. So it becomes x minus x bar all squared. Now, notice the difference between the formulas. So if I'm on y coordinate, then my width becomes my width becomes my y coordinate, and then my depth becomes my x. So instead of bd cube, it becomes db cube, because the depth now is what in the x axis and the width is now what the y. Okay, so this is now equal to, so the depth is now what for the first segment, the depth remains 30 millimeter, so you simply have 30, okay, multiplied by the width, so it becomes width cube. Now instead of the other way around, it becomes width cube, which is 20 cube. So by 20 cube all over 12 plus, see the width times the depth times width, which is 30 by 20. Now in this case, you now subtract, since you're talking about moment of inertia in the y, you now subtract the central distance x from centroid x. And for the first segment, central distance x simply gave us 30. So it becomes 30 minus central in the x, which still remains 26.875. So you simply have 30 minus 26.875 all squared. Okay. So y1 is now equal to, so this is 30 by 20 cube, of course, is 8,000 all over 12 plus 20 by 30, there gives us 600, okay, into 30 minus 26.875, that gives us 3.125 all squared. So this is now equal to, so let's obtain 30 by 8,000 divided by 12, that gives us 20,000 plus, here let's obtain 600 multiplied by 3.125 squared, That gives us 5859.375. So if you add the two of them together, so this simply gives you moment of inertia yy1 is now equal to, so simply add this to 20,000 plus 5859.375. That gives us 28,589.375 millimeter force. So this becomes the moment of inertia in the y-axis for the first segment. So let's put it down here. Y1 is simply 25,859.375. Okay, so that's how you obtain the moment of inertia for the first segment. So next to find Iyy2. Let's do that now and see. I'm going to wipe here off now. So Iyy2, still the same thing. It still becomes b cube all over 12. Please mind these formulas for the y coordinate, plus db into, this becomes also x minus x bar for the second component, all squared. So this is now equal to, for the second component, the depth is 20 millimeter. So put it down, 20, which is d, multiplied by the width. The width is 50 millimeter. Okay, so 50 millimeter cube multiplied by 50 all cube all over 12. Okay, plus 20 by 50 into central distance x for the second component. For the second component, central distance x is 25. Okay, central distance x is 25. So you simply have 25 minus centroid x give us still 26.375 all squared. So you have that. Sorry, this is 875. Okay, 26.875 all squared. So y2 is now equal to, so this is simply 20 by, of course, 50 cube is 125,000 all over 12. Okay, plus 20 by 50 there gives us 1,000 into, so I simply have here 25 minus 26.875. That simply gives us 1.875 minus 1.875 all squared. Okay, so this is now equal to, so let's evaluate 20 times 125,000 divided by 12. That's approximately 208,750 plus, so I have here 1000 multiplied minus 1.875 all squared. That gives us 3515.625. So if you sum them up together, you simply have the value of y2 to now be equal to, so 208,750 plus 3515.625. That gives us 212265.625 millimeter force. So that gives you the moment of inertia for the second segment. And of course, if you add these two moment of inertia together, it will give you the moment of inertia in the y-axis using the parallel axis theorem. So let's do that now and see. I'm going to wipe here. Okay, so from parallel axis, we simply says Iyy is simply Iyy1 plus Iyy2. And we've obtained these values. Iyy1 gave us 2585.375 plus Iyy2, which is 2122 65.625. Okay, so this simply implies that the moment of inertia about the y segment is now equal to simply 238.125 millimeter for. Okay, so this gives you the moment of inertia about the y-axis. All right, guys. So that's how you employ the parallel axis theorem to find moment of inertia for a given composite segment. All right, guys. So in the next video, I will see you with more problems on moment of inertia of composite segment. Thanks, guys, and cheers.